What was the very first living thing in the cosmos? It's a question that stops you in your tracks, not just because it's big, but because it's almost unimaginable. We're talking about the moment life sparked into being, not just on Earth, but possibly somewhere deep in the vast, silent stretches of the universe. What did it look like? How did it come to be? And could we ever truly know? Today, we're embarking on an epic journey to explore not one, not two, but 30 wildly different theories about the universe's first living organism. From the scientifically rigorous to the wonderfully speculative, we're diving headfirst into one of humanity's greatest mysteries. This isn't just a story about biology or chemistry, it's a search for our own cosmic origins. Think about it, every living thing on Earth, from the tallest trees to the tiniest microbes, shares a common ancestor. But what came before that? Was life something that emerged right here on our planet, in a warm little pond as Darwin once pondered? Or did it arrive from somewhere else, carried across the void on comets or asteroids? The scale of this mystery is almost overwhelming, yet it's also incredibly intimate. This is about us, about where we come from, and by extension, why we're here at all. So get ready, because we're about to explore ideas that will stretch your imagination to its limits. We'll look at hydrothermal vents brewing the first organic molecules, ancient RNA worlds where life coded itself into existence, and even the possibility that life began not on a planet, but in the clouds of gas between stars. Some theories are backed by solid evidence, others walk the line between science and philosophy, but each one offers a unique window into one of the most profound questions we can ask. This journey isn't just about answers, it's about wonder, curiosity, and the sheer thrill of exploration. So let's begin. Our first stop on this journey takes us far beyond Earth to the icy, silent realms between stars. This is the world of Panspermia, a theory suggesting that life, or at least its crucial ingredients, didn't originate on our planet at all. Instead, it proposes that microscopic life forms, or the complex organic molecules necessary for life, are cosmic travelers. They hitch rides on comets and asteroids, drifting through the solar system and beyond, eventually landing on young, hospitable worlds like the early Earth, delivering the seeds from which all life would eventually grow. It's a captivating idea that we might all be descendants of interstellar immigrants, but how could something as delicate as life possibly survive such an epic, violent journey? The evidence, surprisingly, is all around us. Scientists have discovered amino acids, the fundamental building blocks of proteins, inside certain types of meteorites that have landed on Earth. These aren't just simple molecules, they're the same complex organic compounds that form the very foundation of life as we know it. Finding them on rocks from space strongly suggests that the raw ingredients for biology are not unique to our planet and can be manufactured in the vast chemical laboratories of interstellar space. Furthermore, we have found incredible organisms right here on Earth that show us just how resilient life can be. They're called extremophiles, microbes that thrive in conditions we once thought were utterly lethal. Some flourish in boiling hot hydrothermal vents at the bottom of the ocean under immense pressure and in complete darkness. Others can be frozen solid for thousands of years and spring back to life when thawed. There are even types of bacteria, like the infamous Deinococcus radiodurans, that can withstand blistering amounts of radiation that would instantly kill almost any other living thing. If such hardy creatures exist on our world, is it really so difficult to imagine a few microscopic spores nestled deep within a protective layer of rock, surviving a long but dormant voyage through the cold vacuum of space, shielded from the worst radiation by their celestial vessel? Panspermia doesn't necessarily answer the ultimate question of how life first began. It simply moves the laboratory from a local pond to a galactic scale. It transforms the question from how did life start on Earth to how did life start somewhere in the cosmos? This theory paints a breathtaking picture of our universe not as a barren void, but as a fertile network, potentially exchanging the spark of life across unimaginable distances, making every planet a potential recipient of a biological inheritance that began light years away. While the idea of cosmic ancestry is thrilling, another compelling theory brings our search for origins much closer to home, or at least to the bottom of our own planet's ancient oceans. Picture a world 4 billion years ago. The young Earth is a turbulent, violent place with a thin, hostile atmosphere constantly bombarded by asteroids. But far below the chaotic surface, at the very bottom of a primordial sea, lies a sanctuary of immense heat and chemical potential. This is the world of deep-sea hydrothermal vents, and many scientists believe it's the most likely cradle for the very first life. These aren't just simple hot springs. Hydrothermal vents, often called black smokers, are towering chimneys on the ocean floor that blast out superheated, mineral-rich water from deep within the Earth's crust. The water can reach temperatures exceeding 700 degrees Fahrenheit, yet it doesn't boil because of the incredible pressure from the ocean above. This creates a bizarre and extreme environment, one that seems utterly inhospitable. But it's within this volatile mix of scalding heat, crushing pressure, and rich chemistry that the magic might have happened. The theory hinges on a concept called chemosynthesis. Instead of using sunlight for energy like photosynthesis does, the earliest life forms could have harnessed the chemical energy flowing from these vents. The water spewing from a black smoker is loaded with dissolved chemicals like hydrogen sulfide, methane, and iron, a potent buffet of potential energy. The rocky, porous surfaces of the vent structures provide countless tiny chambers and catalysts, acting as natural laboratories where these simple molecules could be encouraged to form more complex organic compounds. Over immense spans of time, these building blocks could have assembled into the first self-replicating systems, protected from the violent surface whirled by a mile-thick blanket of water. The most powerful evidence for this theory isn't just in the chemistry, it's in the biology we find there today. Even now, these deep-sea vents are oases of life in the abyssal dark. Entire exotic ecosystems thrive entirely independently of the sun, built around microbes that perform chemosynthesis. Giant tube worms, strange blind shrimp, and unique clams all flourish in this harsh environment, all ultimately dependent on the energy provided by the vent's chemical soup. This proves that complex life can not only survive but truly thrive under the exact conditions that would have existed on the early Earth. It shows us a complete, alternative blueprint for life, one that doesn't require a friendly, sun-drenched pond, but instead draws its power from the planet's own fiery heart. This makes the deep ocean vent a prime candidate for where our oldest ancestor might have taken its first energetic breath. But if the deep sea vents present a dark, high-pressure origin story, another classic theory offers a very different stage for life's first act, a warm, sunlit shallow pond, rich with the chemistry of a newborn world. This is the iconic idea of the primordial soup, a concept that has captured the public imagination for decades and was given profound scientific weight by a groundbreaking experiment in the 1950s. Chemists Stanley Miller and Miller-Urey, working at the University of Chicago, sought to test a fundamental question. Could the basic ingredients of life have been cooked up naturally under the conditions of the early Earth? Their apparatus was deceptively simple, yet its results were revolutionary. They designed a closed system of glass flasks and tubes, filling one flask with water to represent the ancient ocean, and another with a mixture of gases they believed mimicked the early atmosphere, methane, ammonia, and hydrogen. Then they introduced a spark of electricity to simulate the energy from violent lightning storms that would have raged across the primordial sky. They circulated this mixture, allowing the rain to fall back into the ocean, and then they waited. After just 1 week, they analyzed the contents of their miniature world. The results were staggering. The once clear water had turned a murky, organic brown, and within it they found several types of amino acids, the very same building blocks of proteins that form the core machinery of every living cell on Earth today. This experiment provided the first tangible evidence that the complex molecules essential for life could arise from simple, non-living ingredients through completely natural processes. It gave birth to the powerful image of a primordial soup, a nutrient-rich broth in the planet's shallow seas and tidal pools. In this scenario, the sun's ultraviolet light, geothermal heat, and constant electrical energy from lightning strikes provided the power for a planetary-scale chemistry set. Over millions of years, these energy sources would have caused simple molecules to link up, forming ever more complex chains. First amino acids, then peptides, then proteins and other crucial compounds. This rich organic concentrate would have pooled and thickened eventually by some unknown process of self-organization, giving rise to the first structures that could metabolize, replicate, and be considered truly alive. While the miller-urey experiment's specific atmospheric model has been revised by modern science, we now think the early atmosphere was different, composed of carbon dioxide and nitrogen rather than methane and ammonia. The core principle remains powerfully valid. Subsequent experiments using these updated gas mixtures, along with other energy sources like ultraviolet light or shockwaves from asteroid impacts, have successfully produced not only amino acids, but also the nucleobases that make up RNA and DNA. This tells us that the pathway from chemistry to biology is not only possible, but may be a common, almost inevitable outcome given the right conditions and enough time. The theory of the primordial soup suggests that life may be an inherent property of matter and energy, waiting for the right moment and place to stir itself awake. Shifting our perspective from the chemistry of the ocean or the atmosphere, we arrive at a theory that gives credit to the very ground beneath our feet. This is the clay catalyst hypothesis, a fascinating idea that suggests the first steps toward life weren't taken in a soup, but on a solid surface. Imagine the ancient Earth, its landscapes dominated by newly formed minerals and silicate clays. These weren't just dirt, they were intricate, repeating crystalline structures, and they may have provided the essential scaffolding and catalytic power to assemble the first complex molecules of life. The theory hinges on two brilliant advantages that clay offers. First, its surface acts like a natural template. Clay minerals have a layered, repeating pattern of positive and negative charges across their surface. This charged landscape could have acted like a magnetic board, attracting and holding simple organic molecules that were floating in the primordial waters, things like amino acids and nucleotides. As these molecules gathered on the clay, they would have been arranged into precise, orderly patterns, lined up and held in place just like beads on an abacus. This organization is crucial because it overcomes a huge problem in the primordial soup idea. In a vast, dilute ocean, the chance of the right molecules bumping into each other in exactly the right way to form a chain is incredibly slim. The clay surface solves this by concentrating the ingredients and presenting them in an ideal configuration for bonding. The second advantage is catalysis. Many clay minerals are not passive surfaces, they are chemically active. Their crystalline structure can donate or accept electrons, effectively acting as a catalyst to speed up chemical reactions between the molecules stuck to them. This means the clay wouldn't just organize the building blocks, it would also actively encourage them to link together, forming longer and more complex chains like proteins and nucleic acids without itself being consumed in the process. It's a powerful concept, the geological world literally guiding the biological into existence. The first genetic material, a precursor to RNA, might have formed on these mineral templates with the clay's repeating pattern subtly influencing the sequence of the first nucleotides. This idea moves the origin of life from a happy accident in a chaotic broth to a more structured, almost inevitable process driven by the fundamental properties of Earth's geology. It provides a compelling bridge between the non-living mineral world and the complex organic chemistry of life, suggesting our oldest ancestor might not have been a free-floating cell, but a complex molecule slowly growing and replicating on a tiny crystal of clay, a partnership between rock and chemistry that eventually gave rise to everything we know. Yet another possibility takes us away from the solid ground of Earth entirely and into the cold, seemingly empty void between stars. This is the theory of cosmic ancestry in its most direct form, suggesting that the first living organism might not have been a product of our solar system at all. Instead, it proposes that life is a fundamental property of the universe itself, and that its initial spark occurred in the vast molecular clouds that drift through galactic space long before our sun even ignited. Within these colossal clouds of gas and dust, where temperatures hover near absolute zero and densities are almost unimaginably thin, complex chemistry is still at work. We know from astronomical observations that these interstellar nebulae are factories of organic molecules. Using radio telescopes, scientists have identified a stunning variety of compounds in space, including ethanol, formaldehyde, and even simple sugars and amino acids. These molecules form on the surfaces of tiny dust grains, where they are shielded from harsh radiation and can slowly link together. The theory posits that over millions of years, within the protective cocoon of a dense cloud, these molecules could have achieved a level of complexity that crossed the threshold into a very primitive form of life. This wouldn't be life as we picture it, but perhaps a self-organizing, self-replicating molecular system that uses the faint energy of starlight or cosmic rays to sustain its reactions. The journey from this cosmic cradle to a planet like Earth is the next incredible chapter. When a new star system forms from the collapse of such a cloud, these pre-made organic compounds, and perhaps even these primitive living systems, become incorporated into the fabric of comets and asteroids. These celestial bodies then become delivery vehicles, transporting the seeds of life across the young galaxy. When they crash into a wet, rocky world with a stable environment, they inoculate it with the potential for biology. This idea, a specific form of panspermia often called directed panspermia, doesn't just move the origin of life to another planet, it moves it to an entirely different realm, suggesting that the very first organism was a citizen of the galaxy, a product of universal processes that make life an inevitable and widespread phenomenon. While the deep sea vent theory presents a compelling environment, another idea zooms in even further on the specific chemistry happening at those very locations. This is the iron-sulfur world theory, championed by the late chemist Gunther Wechtersheuser. It's a brilliant proposal that shifts the focus from where life began to how it began, suggesting that the very first spark wasn't a self-replicating molecule, but a self-sustaining chemical reaction, a primitive form of metabolism powered by the geology of the hydrothermal vent itself. Imagine not the towering black smokers, but a more subdued, warmer type of vent known as an alkaline hydrothermal vent. These structures are porous, rocky mounds, more like a natural sponge, constantly percolating with warm, chemical-rich fluids. Wechtersheuser's revolutionary idea was that life began not in the open water, but on the solid, electrically conductive surfaces of minerals like iron pyrite, also known as fool's gold. The theory proposes that these mineral surfaces acted as both a scaffold and a catalyst for a cascade of chemical reactions that would eventually become the foundation of all life. The engine of this process is a redox reaction, a fundamental chemical process where electrons are transferred from one substance to another. In this case, the vent fluids provided a rich source of electrons from molecules like hydrogen sulfide, while the ocean water above provided electron acceptors like carbon dioxide. The surface of the iron sulfide minerals provided the perfect meeting place for these reactants, facilitating the transfer of electrons and releasing energy. This energy could then drive the synthesis of more complex organic molecules from simple ingredients like carbon monoxide and hydrogen. It's a powerful concept. The first life was essentially a chemical cycle, a set of reactions feeding off the geothermal energy of the planet, all happening on a tiny crystal of rock. This is where the theory gets truly fascinating. These porous vent structures are filled with a labyrinth of microscopic compartments and channels, creating natural test tubes where these newly formed organic molecules could become concentrated, protected from dilution in the vast ocean. Over immense spans of time, these metabolic cycles could have become more complex and eventually learn to replicate themselves, not through genetics, but by spreading across the mineral surface like a chemical ink blot. The mineral itself, with its repeating crystalline structure, could have provided a crude template guiding the formation of ever more sophisticated reactions. In this view, the first organism was a two-dimensional layer of chemistry thriving on a rock, a partnership between geochemistry and organic chemistry so profound that it eventually gave rise to the three-dimensional, free-living cells we would recognize as life. This idea suggests our most ancient ancestor wasn't a cell, but a rock that learned to metabolize. But perhaps the most provocative variation on this theme takes the idea of cosmic ancestry a step further into the realm of the truly extraordinary. This is the concept of directed panspermia, which proposes that life on Earth may not be the result of a random, natural process, but a deliberate act of seeding by an intelligent civilization from beyond our world. It's a theory that blurs the lines between science and science fiction, suggesting that our ultimate origins might be tied to a conscious decision made by beings we can scarcely imagine. The framework for this idea was laid out in a serious scientific paper in the 1970s by Nobel Prize-winning chemist Francis Crick, one of the co-discoverers of the structure of DNA, and biochemist Leslie Orgel. They weren't claiming this is what happened, but rather posing a profound question. If the emergence of life from non-life on the early Earth seems statistically improbable within the short window of time available, could an alternative explanation be that it was sent here intentionally? They proposed that a technologically advanced civilization, perhaps facing its own impending doom, could have chosen to preserve its biological heritage by packing resilient microorganisms into a sterile spacecraft and directing it toward a promising young planet like Earth. Upon arrival, these microbial ambassadors would have spilled out into the oceans, jump-starting the evolutionary process that eventually led to us. This theory, while highly speculative, is not without its intriguing logic. It sidesteps the immense challenge of abiogenesis, the spontaneous emergence of life from non-living chemistry, by suggesting that difficult step occurred elsewhere, in a different environment and with vastly more time. It also provides a potential answer to the Fermi paradox, the question of why we haven't seen any evidence of other intelligent life if the universe is so vast and old. Perhaps we are the evidence, perhaps our existence is the legacy of a long-vanished progenitor race, and we are now, in a sense, their children, carrying out an experiment they began billions of years ago. The visual is stunning, not just a random meteorite impact, but a sleek, designed vessel piercing the atmosphere of the primordial Earth, deliberately unloading its tiny cargo of hope onto a new world. Of course, this concept ventures into fringe science, and Crick and Orgel themselves treated it as a thought experiment rather than a confirmed hypothesis. The evidence is entirely circumstantial and currently untestable, yet it remains a captivating pillar of cosmic ancestry because it challenges our perspective in a fundamental way. It forces us to consider that the answer to the question, where did the first life come from, might not be found in a chemistry textbook or at the bottom of the ocean, but in the stars, and that the first living organism might have been not a product of chance, but a product of design. Now, let's turn our attention from the deep ocean and the cold of space to the turbulent skies above the early Earth. This brings us to the electric spark theory, a dramatic and visually stunning idea that suggests life's first ingredients were forged in the fiery chaos of primordial lightning storms. Picture the Hadean Eon, a time of incredible violence and beauty. The planet is young, its atmosphere a thick haze of water vapor, carbon dioxide, nitrogen, and methane, constantly rumbling with the energy of intense volcanic activity. And slicing through this toxic, pregnant sky are colossal bolts of lightning, each one a momentary flash of raw, transformative power. This theory gained its foundational support from the famous miller-urey experiment we discussed earlier, but its implications run much deeper than a single lab setup. The genius of that experiment wasn't just in creating amino acids, it was in demonstrating that a simple, abundant energy source, an electric spark, could jumpstart the chemistry of life. On the early Earth, lightning would have been that energy source, and on a planetary scale, every single strike was a tiny, natural version of the miller-urey apparatus, zapping the atmosphere's gaseous soup and triggering reactions that churned out a rain of organic material. But the science has evolved far beyond that initial 1950s experiment. Researchers have since discovered that it isn't just one kind of spark that does the trick. The intense shockwaves from asteroid impacts, which were incredibly common during the late heavy bombardment period, could have generated searing plasma fields that acted like massive lightning strikes, cooking up organic molecules across vast areas. Even the relentless static electricity crackling from volcanic plumes, spewing ash and gases high into the air, would have contributed to this constant planet-wide organic synthesis. The early Earth wasn't just occasionally stormy, it was a continuous, raging generator of the very energy needed to turn simple gases into the precursors of life. The real magic of this process lies in the specific chemistry that a spark unleashes. A bolt of lightning creates a temporary, superheated channel of plasma, reaching temperatures hotter than the surface of the sun. Within this microscopic, fleeting furnace, the tough triple bonds of nitrogen gas are shattered, and molecules like methane and carbon dioxide are broken apart into highly reactive radicals. These fragments are desperate to form new bonds, and as the channel cools, they rapidly recombine into more complex compounds, including formaldehyde and hydrogen cyanide. These two molecules are particularly important. They are the crucial intermediates, the stepping stones that then react further in the atmosphere and in rainwater to form amino acids, sugars, and the nucleobases for RNA and DNA. Imagine this process not as a single event, but as a constant planetary drizzle of possibility. For millions of years, this electric energy catalyzed a non-stop production line, with the sky acting as the reactor vessel and the oceans below becoming the collecting bowl. The warm, shallow pools and coastal waters would have steadily concentrated this organic rain, creating that rich primordial soup where the next steps toward self-replication could slowly, patiently unfold. The electric spark theory gives us a powerful image of creation born from destruction, where the violent, chaotic forces that shaped our young planet were also the very same forces that gently assembled the first delicate pieces of life. While our journey has taken us from the ocean depths to the interstellar clouds, there is a theory that suggests we need to look no further than the ground directly beneath our feet, but we have to look very, very deep. This is the deep Earth hypothesis, a compelling idea that proposes life did not begin on the planet's surface, but was instead born in the crushing, hot, pitch-black darkness of the Earth's crust itself, several miles underground. To understand this, we have to completely rethink what a habitable environment means. On the surface 4 billion years ago, the world was a terrifying place, constantly bombarded by asteroids and bathed in lethal levels of ultraviolet radiation from a young, violent sun. It was for any fledgling life form an apocalyptic nightmare, but deep below, within the fractured bedrock of the planet's crust, there was a stable sanctuary. This subterranean world was insulated from the chaos above, maintaining a constant temperature, and crucially, it was filled with two things every origin story needs: water and energy. The energy down there didn't come from the sun, but from the planet's own inner fire and its radioactive heart. Radioactive elements like uranium, thorium, and potassium are naturally present in rocks. As these elements decay, they release a steady, gentle trickle of energy and radiation. This might sound destructive, but for the right kind of chemistry, it's a powerful catalyst. This radiolytic energy could have broken apart water molecules trapped in porous rock, creating hydrogen gas and reactive oxygen compounds. Certain ancient iron-rich minerals like olivine can also react with water in a process called serpentinization, which releases even more hydrogen and heat. This creates a continuous geothermal energy source perfect for driving chemical reactions. In this pressurized, heated, mineral-rich environment, the pores and fractures within rocks become microscopic chemical reactors. These tiny chambers could have concentrated simple organic molecules, allowing them to link into longer chains, protected from being diluted or destroyed. The theory suggests that the first metabolic pathways, the chemical routines that define life, emerged in these isolated pockets, with primitive organisms learning to eat the hydrogen and other chemicals produced by the rocks themselves, a process called chemosynthesis that we see in extremophiles today. And this is where the theory moves from a historical possibility to a modern-day reality. We now know that this deep biosphere is not just a theory, it's a vast living world. Scientists have discovered microbes thriving several miles underground, in places we once thought were utterly sterile. These incredible extremophiles live in the pores of rocks, in groundwater isolated for millions of years, and near hydrothermal systems deep within mines. They don't just survive, they form entire ecosystems completely independent of the sun's energy, subsisting on a diet of hydrogen, sulfur, and minerals provided by the geology around them. Their existence is powerful proof that the ancient, deep Earth could have been a more than adequate cradle for life, offering a safe, stable, and energy-rich haven where biology could take its first, fragile steps away from geochemistry, forever changing the story of our planet. Now, let's journey from the planet's fiery depths to its frozen poles, and even out to the icy comets drifting in the void. This is the theory that life didn't begin in warmth but in cold, that freezing environments were the perfect nursery for the universe's first organism. It's a counterintuitive idea. We often think of ice as still and lifeless, but this theory suggests that the cold didn't preserve life, it created it by providing a unique set of conditions that the warm little pond simply couldn't offer. The challenges on the early Earth's surface were immense, and one of the biggest was ultraviolet radiation from the sun, which was powerful enough to break apart the delicate organic molecules that are life's building blocks. A freezing environment offers a brilliant solution, a protective shield. A layer of ice, even just a few inches thick, can act as a natural sunscreen, filtering out the most damaging wavelengths of UV light. This would have created a safe haven underneath, where fragile compounds could accumulate and interact without being instantly destroyed. Imagine a pond on the early Earth periodically freezing over. The surface ice seals and protects the chemical cocktail below, while the chaos of the surface world rages harmlessly overhead. But the cold does more than just protect. It actively encourages the chemistry of life through a remarkable process called concentration. As water freezes, it pushes impurities out of the forming crystal structure. If you have a solution containing amino acids and other organic molecules, the freezing process will force them out of the ice and into the tiny, ever-shrinking pockets of liquid water trapped between the ice crystals. In these microscopic chambers, the molecules become incredibly concentrated, far more than they ever could be in a vast, open ocean. This massively increases the chances that they will bump into each other and form the bonds needed to create longer chains like proteins and RNA. It's like a natural laboratory using freezing temperatures to concentrate the reagents and run the experiment. Furthermore, the cold itself can be a catalyst. We often think chemical reactions need heat to speed up, but that's not always the case. extremely cold temperatures can actually stabilize certain intermediate molecules that would be too unstable to exist in a warm environment, allowing for slower, more deliberate and precise reactions to occur. This slower pace might have been absolutely critical for allowing the first clumsy, inefficient self-replication processes to emerge and refine themselves without falling apart. The intense cold of space found on icy comets and moons could have served as the ultimate cryogenic laboratory, where these slow-cook chemistry experiments had millions of years to play out before a comet's collision delivered THEIR Chinese letter to a young planet like Earth. This theory beautifully reframes the icy reaches of the cosmos not as barren wastelands, but as silent, patient cradles where the first stirrings of life could peacefully come together. This idea of chemistry building upon itself brings us to a theory that is as elegant as it is profound, one that suggests life's origins lie not in a single miraculous molecule, but in the emergent property of a self-sustaining network. This is the world of autocatalytic sets. Imagine a group of different chemical compounds, each one not only forming through a reaction but also, crucially, helping to create another member of the group. It's a closed loop of creation, a chemical circle of life where the whole network sustains itself, becoming far more resilient and complex than any of its individual parts could ever be alone. The core of this theory moves the goalposts for the definition of life's beginning. Instead of searching for the first self-replicating molecule like RNA, which is a tremendously high bar to clear, it proposes that the first sign of life was a self-replicating system, a primitive form of metabolism that emerged from the simple laws of chemistry. In this view, genetics and replication came later as a sophisticated tool to stabilize and manage a metabolic process that was already underway. The first spark of life wasn't a single note but an entire chord. To understand how this works, picture a simple example with just two hypothetical molecules. Let's call them molecule A and molecule B. Imagine that molecule A can catalyze or speed up the chemical reaction that creates molecule B. Now imagine that molecule B, in turn, can catalyze the reaction that creates molecule A. Individually, they are just chemicals, but together they form a tiny, self-reinforcing cycle. If you have a little bit of A, it helps make more B. That new B then helps make more A. This positive feedback loop would cause the concentrations of both molecules to grow exponentially from a tiny starting point, a clear sign of a self-sustaining process. Now expand this idea from a simple pair to an entire web. Add a molecule C that is created by B and helps create A. Add a molecule D that is created by A and helps create C. Soon, you have a dense, interconnected network where every member's existence is supported by the actions of the others. This network is an autocatalytic set, a community of molecules that collectively catalyzes its own formation and growth. The set itself becomes a distinct entity, maintaining its composition and growing more complex over time, effectively acting as a very primitive, non-genetic form of life. It's a stunningly beautiful concept, life as a cooperative chemical society. The most compelling evidence for this theory doesn't come from a lab recreation of the primordial Earth, but from pure mathematics and computer science. Researchers have used software to model vast networks of random chemical reactions. They assign random catalytic properties to different molecules and then set the system in motion. Time and time again, these simulations show that under the right conditions, autocatalytic sets spontaneously emerge from the chaos. They are not a rare fluke, they are a natural, almost inevitable outcome of complex chemistry. This tells us that the leap from a disorganized chemical soup to an organized, self-perpetuating system might be a fundamental property of the universe, waiting to happen wherever the ingredients and conditions are right. It suggests that the path to life may be paved with cooperation right from the very first moment. While the autocatalytic set theory paints a picture of a self-sustaining chemical network, it leaves a crucial question unanswered. How did this delicate web of reactions protect itself from a disruptive and diluting environment? This brings us to a theory that provides a stunningly elegant solution, one that suggests the first living organism wasn't a molecule or a reaction, but a tiny, self-assembling bubble. This is the lipid world hypothesis, a fascinating idea that gives center stage to one of life's most fundamental structures, the cell membrane. For life as we know it to exist, there must be a boundary, a barrier that separates the intricate internal machinery from the chaos outside. In every modern cell, this barrier is the lipid bilayer, a double wall of fatty molecules that is impermeable to water but allows for the selective transport of nutrients and waste. The lipid world theory proposes that this fundamental structure wasn't a late evolutionary invention. It was the very starting point. The first step toward life may have been the spontaneous formation of these microscopic containers, which then provided the perfect sheltered environment for those complex autocatalytic networks to flourish and evolve. The beauty of this theory lies in the remarkable properties of lipids themselves. These fatty molecules have a natural duality. One end is hydrophilic, meaning it's attracted to water, while the other end is hydrophobic, repelled by water. When you have a collection of these lipids in an ancient watery environment, they don't just float around randomly, they self-organize. To escape the water, the hydrophobic tails huddle together, while the hydrophilic heads face outward, interacting with the surrounding liquid. The most stable, energy-efficient shape this arrangement can form is a sphere, a closed bubble called a vesicle, with a double layer of lipids creating a protective wall. This isn't a hypothetical process. Scientists can easily recreate it in a lab today by simply shaking a solution of lipids in water. Under the right conditions, they spontaneously form these perfect little containers. Now imagine the primordial Earth with its tidal pools and shallow seas rich with organic molecules, including these simple lipids. Waves, temperature changes, and currents would have provided the energy to constantly form and break apart these vesicles. But here's where the magic happens. These lipid bubbles aren't just passive containers, they are active participants. They can grow by incorporating new lipid molecules from their environment, and when they get too big, they become unstable and divide, almost like a form of very primitive reproduction. Even more astonishingly, they can selectively trap molecules from the surrounding water inside their protective sphere. If the outside world contained a budding autocatalytic set, a group of molecules that catalyzed each other's formation, getting trapped together inside a lipid vesicle would have been a revolutionary event. Inside this tiny, sheltered laboratory, the chemical network would be protected from dilution and could operate far more efficiently. The vesicle membrane itself could even act as a catalyst, its surface providing a staging ground for reactions. Different vesicles would have trapped different combinations of molecules, creating a vast experiment in early evolution. The most successful vesicles, those that housed networks which produced molecules that strengthened the membrane or aided in division, would have persisted and multiplied. Over time, these two systems would have become inextricably linked, the internal chemistry supporting the membrane's growth and the membrane protecting the internal chemistry. This partnership between container and contents could have been the true dawn of the cell, and by extension, the dawn of life as a distinct, self-contained entity. The lipid world theory doesn't just give us a location for life's origin, it gives us a protagonist, the humble, self-assembling lipid vesicle that learned to divide and conquer the ancient seas. Leaving behind the icy domains and self-organizing bubbles, we arrive at a theory that feels both primal and powerfully elemental, the volcanic hot spring. This idea returns us to the solid ground of the early Earth, but to a very specific and dynamic kind of landscape, a geothermally active field where the planet's internal heat breaches the surface in a spectacle of steam, boiling water, and mineral-rich pools. It's a scene of constant change and immense energy, and many scientists believe these locations were the perfect natural laboratories for assembling the first molecules of life. The strength of this theory lies in its combination of several crucial ingredients. A terrestrial hot spring is not a single environment system. It's a gradient offering a full spectrum of conditions within a very small area. At the very center, where superheated water erupts from the vent, temperatures can be lethally high. But just inches away, as the water flows outward and begins to cool, it passes through a perfect Goldilocks zone, warm but not too hot. This thermal gradient is vital because it allows for a huge variety of chemical reactions to occur simultaneously. The intense heat at the source can drive the formation of new organic compounds, while the slightly cooler margins provide a stable environment where those delicate new molecules can link together into more complex structures without immediately being destroyed. What truly makes these springs special, however, is their incredible mineral richness. The hot water rising from deep underground dissolves a cocktail of elements from the surrounding rock. Things like silica, sulfur, phosphorus, and various metal ions. As this mineral-laden water reaches the surface and cools, these elements precipitate out, forming intricate crystalline structures and, most importantly, clay minerals. This is where the hot spring theory connects beautifully with the clay catalyst hypothesis we explored earlier. The constantly flowing water would have circulated simple organic molecules through these newly formed mineral scaffolds. The charged surfaces of clays could have concentrated these molecules and acted as catalysts, encouraging them to form longer chains like peptides and strands of nucleic acids. The spring acts as both a factory and an assembly line. Recent experimental research has brought this theory to life in stunning detail. Scientists have created lab-based simulations of these ancient hot spring environments called warm little ponds. They cycle the conditions, wetting and drying the mixture of water, simple organic compounds, and minerals, all while applying a gentle heat source. The results have been extraordinary. This wet-dry cycling proves to be a powerful engine for synthesis. The drying phase concentrates the reactants, forcing molecules into close contact and driving dehydration reactions that are essential for forming the bonds in proteins and RNA. The subsequent rewetting phase then allows new materials to flow in, refreshing the system for another round. This continuous process has been shown to efficiently create the building blocks of life and even promote the formation of lipid vesicles that can encapsulate them, creating convincing prototypes of the very first protocells. These aren't just random chemicals, they are the fundamental structures of biology, emerging naturally from the rhythm of the spring. The visual is incredibly compelling. Imagine a steaming, multi-hued pool on the primordial Earth. In its vibrant, mineral-rich waters, fatty acids spontaneously gather into hollow spheres. Nearby, on the intricate surfaces of freshly formed clays, amino acids link into chains and nucleotides align into primitive genetic codes. The natural flow of the spring then washes these new creations together, and during a dry period, they become trapped inside a newly formed vesicle. When the rains return and the pool refills, that sealed container finds itself floating in a rich nutrient bath, a protected microenvironment where its internal chemistry can begin to evolve in isolation. This theory provides a complete narrative from geochemistry to biochemistry, all within the dynamic, life-giving embrace of a volcanic hot spring. But to find a truly universal laboratory, we must journey away from our planet entirely and into the vast, silent spaces between the stars. This brings us to a theory that suggests the very first steps toward life didn't happen on any world, but on the tiniest of platforms adrift in the cosmic ocean, interstellar dust grains. Envision a colossal nebula, a stellar nursery light years across, glowing with ethereal light. It appears as a beautiful, empty cloud, but it is anything but empty. It is a seething soup of gas and, most importantly, countless trillions of microscopic solid particles, silicate and carbonaceous, dust no larger than a fraction of a micron. forged in the hearts of ancient stars and scattered across the galaxy. In the deep, cold, and near-perfect vacuum of space, these minuscule motes of dust become far more than just specks. They become the most fundamental solid surfaces in the universe, and they serve a critical purpose. The vastness of space is the enemy of chemistry, for two molecules floating freely to meet and react is incredibly unlikely, but these dust grains solve that problem. They act as a meeting ground, a solid anchor where atoms and simple molecules like carbon monoxide, hydrogen, and water can slowly drift in and stick to the surface, a process known as adsorption. Suddenly, instead of being light years apart, these potential reactants are neighbors held in close proximity on a tiny, frozen stage. This is where the true alchemy begins. While these nebulae are cold, they are not inert. They are bathed in the relentless energy of ultraviolet light from nearby young stars. This UV radiation doesn't just illuminate the cloud, it acts as a power source, breaking the bonds of the molecules frozen to the dust grains and creating highly reactive fragments known as radicals. These radicals, now trapped side by side on the grain's surface, are desperate to form new bonds. With the gentle warmth of a nearby star or even the faint energy of cosmic rays, they begin to hop around on their dusty home, eventually finding a partner and reacting to form new, more complex molecules. This process, repeated over millions of years, can build molecules of startling complexity right there in the void. We know this isn't just speculation because our telescopes have confirmed it. Using radio astronomy, scientists have identified a veritable menagerie of organic molecules in these molecular clouds, including ethanol, acetic acid, and even the simplest amino acid, glycine. The dust grain provides the surface, the cold temperature keeps the fragile product stable, and the UV radiation provides the energy to drive the reactions. It's a slow, cold, and meticulous form of chemistry, but it has the one thing the early universe had in abundance: time, epochs upon epochs of it. This theory paints a breathtaking picture of our galaxy not as a barren void, but as a sprawling, natural chemistry set where the fundamental building blocks of biology are manufactured on a cosmic scale, long before any planets have even formed, ready to be delivered to new worlds and become part of their story. Now we venture into one of the most speculative and mind-bending frontiers of this entire quest, the idea that the spark of life wasn't just a chemical event but a quantum one. This theory proposes that the strange, almost magical rules of the quantum world, a realm where particles can be in two places at once or tunnel through solid barriers, weren't just bystanders to the origin of life. They might have been essential actors, providing a critical advantage that allowed the first living systems to overcome seemingly impossible odds. To grasp this, we have to step away from our everyday, classical view of physics. In our macroscopic world, things are predictable. A billiard ball hits another and sends it in a specific direction. Chemistry often works the same way. We imagine molecules as little balls that need to collide with enough force and in the right orientation to react. For the first, incredibly inefficient protoenzymes and metabolic cycles, this billiard ball model presents a huge problem. The chances of all the right molecules meeting in exactly the right way to form a complex, self-sustaining network seem astronomically low. It's like expecting a tornado to blow through a junkyard and assemble a perfectly working spacecraft. Quantum biology suggests there might be a shortcut, a way around this problem of improbability. One of the most discussed quantum effects in this context is tunneling. In the quantum world, a particle doesn't always need the energy to go over an energy barrier. There's a probability it can simply appear on the other side, as if it dug a tunnel straight through. This isn't a theory, it's a well-documented phenomenon that explains how nuclear fusion powers the sun. Now, apply that to a biochemical reaction in a primordial soup. A proton, a crucial component in countless reactions, might need to jump from one molecule to another to create something new. Classically, it might not have the energy to make that jump. But through quantum tunneling, it could effectively cheat, tunneling through the energy barrier to complete the reaction far more quickly and efficiently than should be possible. This quantum cheat code could have dramatically accelerated the early, clumsy steps of metabolism, making the transition from chemistry to biology not a near impossible lottery win, but a much more probable event. Another fascinating quantum effect is coherence. In our world, things are localized. You are either here or there, but in the quantum realm, a particle can exist in a state of superposition. It can be in multiple places or states at the same time, essentially exploring all possible pathways simultaneously. Some researchers speculate that this property could have allowed the first light-harvesting molecules, perhaps even in those icy cosmic nurseries we discussed, to achieve astonishing efficiency in capturing energy. Instead of a photon of light having to hit one specific molecule, a quantum coherent system could essentially sample a wider area, finding the most efficient path to transfer that energy to where it was needed for a chemical reaction. This isn't just wild speculation. We see evidence of long-lasting quantum coherence in the photosynthetic systems of green plants today, suggesting nature has indeed harnessed these spooky effects to master the conversion of sunlight into energy. Of course, this is a highly speculative and fiercely debated field. The warm, wet, and chaotic environment of a living cell seems like the last place delicate quantum states could survive without collapsing. Critics argue that any such quantum effects would be instantly destroyed by their surroundings, a process called decoherence. Yet, the fact that we are finding clear signatures of quantum mechanics in modern biological processes forces us to ask a profound question. Is this a later evolutionary refinement, or is it a haunting echo of life's very first moments? Perhaps the conditions in a protected microscopic pore within a clay deposit or deep inside a lipid vesicle were just isolated enough for these quantum advantages to flicker into existence, providing that crucial, inexplicable edge that tipped the balance from a complex chemical system to something truly, vibrantly alive. It's a theory that connects our biological selves to the most fundamental fabric of the universe, suggesting that life itself might be one of the universe's most sophisticated quantum experiments. Yet another perspective weaves together the strengths of both the deep-sea vent and the terrestrial spring into a single dynamic model. This is the hydrothermal field theory, which proposes that the true cradle of life wasn't one static environment, but the vibrant, ever-shifting interface between land and sea on the early Earth. Picture a volcanic coastline 4 billion years ago, a place where the planet's immense geothermal energy meets the vast nutrient reservoir of the ocean. Here, you wouldn't find just one type of vent. You'd find an entire spectrum of them towering black smokers on the seafloor, shallower warm springs bubbling up through porous rock, and geysers erupting right at the water's edge, all creating a sprawling, interconnected chemical landscape. The sheer diversity of this field is its greatest asset. It offers every conceivable condition a budding chemical network could need. The superheated depths provide a constant source of energy and raw minerals. The sun-warmed shallows offer a gentler environment for more delicate molecules to assemble. And crucially, the area in between is subject to the constant rhythm of tides, volcanic activity, and rainfall, creating a world of perpetual change. It is this very fluctuation that the theory identifies as the engine of creation. Where a stable environment might allow chemistry to plateau, a dynamic one constantly pushes it forward, forcing adaptation and innovation. The most critical process this environment enables is polymerization, the linking of small organic molecules into long, complex chains like proteins and RNA. This is a dehydration reaction, meaning it requires the removal of a water molecule to form a new bond. In a constantly wet environment, this is chemically difficult. The reaction is constantly fighting against the surrounding water that wants to break the bond apart. This is where the wet-dry cycles become absolutely essential. Imagine a tidal pool fed by a geothermal seep. At high tide, it's inundated with fresh, mineral-rich water, collecting a new batch of simple building blocks. As the tide recedes or the sun beats down, the pool partially evaporates, concentrating all those molecules together. In this increasingly dense, almost syrupy solution, the molecules are forced into intimate contact, and the loss of water actively drives the dehydration synthesis that links them into polymers. Then the tide returns or rain falls, refreshing the pool with new nutrients and washing the newly formed compounds into a new area to begin the cycle again. This isn't a one-time event, it's a relentless planetary scale pump running countless times a day for millions of years, tirelessly building complexity. This theory elegantly solves multiple problems at once. The hydrothermal field provides a continuous supply of building blocks and energy. The tidal and geothermal cycles provide the mechanical energy for concentration and reaction. And the incredible diversity of micro-environments within the field means that if a promising reaction fails in one pool, perhaps it gets too hot or is washed away, a nearly identical process might be succeeding just meters away in a slightly different setting. It creates a massive, natural experiment in probiotic chemistry, with countless parallel trials running simultaneously, dramatically increasing the odds that one of them would eventually stumble upon the winning formula that could sustain itself, replicate, and finally cross the threshold into what we would call life. It suggests that life didn't emerge from a single, perfect spot, but from the entire vibrant, chaotic, and creative borderland where the young Earth's fire and water were locked in their eternal dance. While Panspermia offers the grand vision of life itself traveling between worlds, a more specific and powerfully supported theory suggests something slightly different but no less profound. Perhaps it wasn't living cells that rained down on the early Earth, but the entire chemical starter kit required to build them. This is the concept of meteorite delivery, and the evidence for it is literally written in stone, preserved in some of the oldest rocks to ever fall from our skies. To understand this, we must look at a specific class of space rocks known as carbonaceous chondrites. Unlike the more common iron or stony meteorites, these are primitive, relatively unaltered relics from the very formation of our solar system 4.6 billion years ago. They are cosmic time capsules, and one in particular stands as a legendary piece of this puzzle, the Murchison meteorite. In 1969, this rocky object exploded in the atmosphere and scattered fragments over Murchison, Australia. Its arrival was a gift to science, providing a pristine sample of the materials that were floating around in our young solar system, long before the Earth had even finished forming. When scientists began to analyze the Murchison meteorite, they were utterly astonished. It wasn't just a simple rock, it was an organic chemist's treasure chest. Inside, they found a stunningly diverse array of the fundamental building blocks of life. This included over 90 different amino acids, the very same molecules that form the proteins which power every biological process in our bodies. But the discovery didn't stop there. The Murchison meteorite also contained nucleobases, the information-carrying components of RNA and DNA, along with sugars, and a complex mixture of other hydrocarbons. Crucially, many of these amino acids were of a type not common in terrestrial biology, proving they were not the result of earthly contamination, but were truly extraterrestrial in origin. This tells us something monumental. The complex organic chemistry necessary for life is not unique to our planet. It was happening on an industrial scale in the vast protoplanetary disk that swirled around our infant sun. The processes we've discussed: chemistry on interstellar dust grains, reactions in the icy mantles of comets, were manufacturing these compounds everywhere. And then, during the period known as the Late Heavy Bombardment, around 4 billion years ago, the inner solar system was absolutely pummeled by countless asteroids and comets. Earth, being the largest gravitational target in the neighborhood, would have received a truly staggering delivery of this organic material. It wasn't a gentle drizzle, it was a monsoon of prebiotic ingredients from space. This theory doesn't necessarily conflict with ideas like the primordial soup or hydrothermal vents. It supercharges them. Imagine the early Earth's oceans. The classic primordial soup theory suggests that life's ingredients were cooked up locally in the atmosphere and oceans. But what if that soup wasn't just made from scratch with local ingredients? What if it was a ready-made stew to which a colossal delivery of extra-rich, pre-packaged organic stock was added from space? The meteorites and comets that bombarded our planet wouldn't have just delivered raw materials. They would have delivered them in incredibly high concentrations, essentially seeding the planet's pools and oceans with a concentrated broth of life's building blocks. This massive external delivery could have dramatically accelerated the entire process, providing a rich, pre-made inventory of complex molecules that simply needed the right environment, a warm little pond, a hydrothermal vent, a tidal zone, to finally assemble into the first living organism. It suggests that while Earth provided the comfortable kitchen, the universe might have kindly provided a big part of the grocery list. While our journey has taken us to the depths of the ocean and the cold of space, we now turn to the most abundant and powerful energy source in our solar system, the Sun itself. This is the theory of photochemical origins, which suggests that the fierce, untempered ultraviolet light bathing the young Earth wasn't a threat to be avoided, but the very spark that ignited the chemistry of life. 4 billion years ago, our star was younger and more violent, emitting intense levels of UV radiation that would be lethal to most modern life. Yet, in the absence of a protective ozone layer, this constant barrage of high-energy photons may have been the essential catalyst that drove simple molecules to assemble into life's complex precursors, right in the planet's atmosphere and on its sun-drenched surface. This idea finds its foundation in the same brilliant logic that made the miller-urey experiment so revolutionary. Energy drives complexity, but instead of lightning providing the jolt, here the energy was delivered by light. The process begins with the primitive atmosphere, a thick haze of gases like water vapor, carbon dioxide, nitrogen, and possibly some methane and ammonia. As UV photons from the sun slam into these molecules, they carry enough energy to break their chemical bonds, shattering them into highly reactive fragments known as free radicals. These radical species are desperate to form new bonds, and in the chaotic soup of the atmosphere, they rapidly collide and recombine into new, more elaborate configurations. This relentless cycle of destruction and creation, powered by sunlight, could have acted as a planet-scale factory, tirelessly producing a rain of organic material. The evidence for this isn't just theoretical, it has been demonstrated convincingly in the laboratory. Scientists have recreated the proposed primordial atmosphere in sealed reaction chambers, but instead of using an electric spark, they use lamps that simulate the UV output of the young sun. The results are remarkably effective. These experiments consistently show the formation of key biological building blocks, including amino acids and the nucleobases that form RNA and DNA. The process is particularly efficient when the reactions occur not in a free gas but on solid surfaces. Imagine fine particles of clay or silicate dust suspended high in the ancient atmosphere. These tiny particles could have provided a stable stage where the shattered molecular fragments could adhere, be held in close proximity, and be encouraged by the mineral's surface chemistry to link up into more complex chains before eventually falling back to Earth. This paints a vivid picture of the early Earth not as a hostile environment for chemistry, but as an ideal photochemical reactor. The entire sky was its chamber, the sun was its energy source, and the constant circulation of the atmosphere ensured a continuous production cycle. The organic compounds synthesized in the upper atmosphere would have been carried by winds and eventually washed down into the oceans and lakes by rainfall, creating a steady, planet-wide delivery of ingredients to the primordial soup below. This theory beautifully complements other ideas. The UV-driven atmosphere could have been the primary source of the raw materials that then became concentrated in tidal pools, organized on clay sheets, or encapsulated within lipid vesicles, providing the rich, pre-made inventory necessary for the next steps toward life to occur. It suggests that life's journey may have begun with a sunbeam, transforming the simple chemistry of the air into the first whispers of biology. But what if the very first spark of life wasn't a chemical, but a spark of electricity? This brings us to a theory that focuses not on the ingredients, but on the power source, proposing that the first organism harnessed a fundamental force of nature in a way that still powers every single cell on Earth today. This is the alkaline vent theory, a brilliant and specific model that transforms the deep sea vent from a simple chemical reactor into a sophisticated natural battery. Imagine not the scorching, sooty black smokers, but a gentler, more mysterious type of structure known as a white smoker or an alkaline hydrothermal vent. These are vast, labyrinthine mounds, sometimes hundreds of feet high, made of a porous, greenish mineral called serpentinite. They form where seawater seeps down through cracks in the ocean floor, is superheated by the Earth's magma, and reacts with the underlying mantle rock. This process creates a warm, highly alkaline fluid rich in hydrogen and other dissolved minerals, that then percolates back up and slowly flows out of these rocky chimneys. The magic happens where this warm, alkaline fluid meets the cold, acidic water of the early ocean. This meeting point creates a fundamental and powerful imbalance, a difference in the concentration of protons, what chemists call a proton gradient. In every living cell on Earth, from the smallest bacterium to the neurons in your brain, energy is stored and utilized through precisely these kinds of proton gradients across a membrane. It's the universal currency of biological energy. The alkaline vent theory suggests that this system isn't a late evolutionary invention. It was the very first engine provided freely by the geology of the early Earth. The porous, mineral-rich walls of the vent are the key to this process. They aren't solid. They are more like a natural sponge, filled with a network of microscopic pores and channels. These tiny compartments have walls that are semi-permeable, acting as the world's first membranes. As the alkaline vent fluid and the acidic ocean water intermingle through these walls, protons naturally flow from the acidic ocean side into the alkaline vent fluid side, following their gradient. This flow of protons is a form of energy, much like water flowing downhill through a turbine. Scientists believe this natural, continuous energy flow could have been harnessed by early chemical systems to drive essential reactions. For instance, this proton motive force could have provided the power to stitch simple carbon molecules together into more complex organic compounds, a process called carbon fixation. It could have charged up molecules like pyrophosphate, a primitive precursor to the universal energy currency ATP that all life uses today. The vent's microcompartments provided the perfect sheltered environment where these delicate energy harnessing systems could develop and refine themselves, protected from the chaotic open ocean. Over immense spans of time, the theory suggests that organic molecules learn to form their own membranes around these natural proton gradients, eventually becoming independent enough to leave the mineral scaffold behind, taking their built-in electrical power source with them. This means the first free living cell may have essentially been a tiny, self-contained version of the alkaline vent itself, carrying the legacy of that primordial deep-sea energy within its very structure. Now, let's consider the very ground we walk on not as a passive stage, but as an active participant in life's origin story. This brings us to a theory that gives a starring role to the most common minerals on Earth. Imagine the chaotic primordial soup, a dilute mixture of organic molecules floating in the ancient seas. The odds of them randomly bumping into each other in just the right way to form something complex are astronomically low. But what if they didn't have to rely on chance alone? What if they had a guide, a sort of molecular cheat sheet provided by the planet itself? This is the essence of the silicate surfaces theory, which proposes that the intricate crystalline structures of common minerals like silica and zeolites acted as templates, literally shaping the first steps toward organized life. The power of this idea lies in the natural architecture of these minerals. Silica, for instance, is the main component of sand and quartz, and zeolites are microporous minerals often used today in water filters and catalysts. Their surfaces are not smooth and featureless. At the atomic level, they are intricate landscapes of positive and negative charges arranged in precise, repeating patterns. This ordered structure is the key. In the ancient waters, simple organic molecules like amino acids and nucleotides would have been drawn to these charged surfaces. It's a bit like how a magnet organizes iron filings. The molecules aren't just sticking randomly. They are aligning themselves into specific positions dictated by the mineral's crystalline lattice. This overcomes the enormous problem of dilution and random motion, organizing the building blocks and holding them in place, perfectly positioned to react with their neighbors. This isn't just about organization, it's also about catalysis. Many silicate minerals are naturally catalytic, meaning they can significantly speed up chemical reactions without being consumed themselves. A molecule held on a charged mineral surface is often in a slightly stressed or activated state, making it far more likely to form a bond with the molecule next to it. This catalytic effect could have driven the polymerization of amino acids into protein-like chains and nucleotides into the first rudimentary strands of genetic material. The mineral's surface isn't just a stage, it's a director actively encouraging the actors to perform. Perhaps the most fascinating implication of this theory is the concept of information transfer. The repeating pattern of atoms on a crystal face could have provided a crude physical template, influencing the sequence in which nucleotides link together. Imagine a specific pattern of bumps and divots on a zeolite surface that just happens to favor the attachment of adenine, then guanine, then cytosine. This isn't a genetic code, but it could be a primitive physical precursor to one, a way for the non-living world to impart a faint whisper of order onto the emerging organic world. The first genetic molecule might not have been a free-floating strand of RNA, but a chain of nucleotides growing along a crystalline surface, its sequence subtly influenced by the atomic geography of the rock beneath it. In this view, life's incredible complexity didn't emerge from pure chaos, but was gently shepherded into existence by the silent, ordered architecture of the Earth's most humble minerals. But what if the very first energy currency of life wasn't the sophisticated molecule we know today, but something far simpler and more rugged, forged in the fiery conditions of the early Earth? This brings us to a deeply insightful theory that focuses not on genetics or cells, but on pure, raw power, the thioester world. To understand this, we need to look at the universal energy coin of all modern life, ATP, or adenosine triphosphate. Inside your cells right now, ATP is constantly being spent and recharged to power every thought, every movement, every heartbeat. But ATP is a complex molecule, a masterpiece of evolution. The thioester world theory asks a brilliant question. What came before this perfected currency? What was the primitive, rough around the edges prototype that first allowed energy to be captured, stored, and spent? The answer, proposed by the renowned biochemist Christian de Duve, lies with a much humbler class of molecules, thioesters. These are energy-rich compounds formed between a carboxylic acid and a thiol, which is a molecule containing sulfur. Their magic is in their high-energy bond. This bond is unstable and eager to break, and when it does, it releases a burst of energy that can drive other chemical reactions that would otherwise be impossible. Think of it like a coiled spring. A thioester is a spring tightly wound and ready to snap, and that release of tension is what does the work. This is the fundamental principle of metabolic energy, and thioesters are exceptionally good at it. So why would these specific molecules be the pioneers? The theory points directly to the environments we've already discussed, particularly the deep-sea hydrothermal vents. These vents are not only rich in iron and sulfur, but also spew out hydrogen sulfide and other sulfurous compounds. The early Earth was a world dominated by sulfur chemistry, making thioesters a highly probable and abundant product of the reactions happening around these mineral-rich vents. They wouldn't have been a rare delicacy, they would have been a common, off-the-shelf energy source readily available for any primitive chemical network to exploit. The true elegance of the thioester world is how it provides a plausible pathway for the emergence of the very first metabolic cycles, the sets of reactions that define a living system. Imagine a simple loop of reactions where a thioester's energy is used to activate a molecule, perhaps joining two carbons together. The product of that reaction could then go on to regenerate another thioester, closing the loop and creating a self-sustaining cycle that feeds on simple geochemical ingredients like carbon monoxide and hydrogen. This is a primitive form of metabolism, a chemical engine that turns over and generates order from chaos, all powered by the simple, relentless snap of thioester bonds. It suggests that the first stirrings of life were not about information but about energy management, a system that learned to eat, not to remember. Before there was a genetic code to guide the process, these thioester-driven cycles could have provided the thermodynamic push, creating a stable, self-reinforcing chemical reality from which all the later complexities of genetics and replication could eventually emerge. But if interstellar dust grains provided the workshop and meteorites the raw materials, what was the vehicle that could have delivered this precious cargo across the solar system without destroying it? This brings us to a theory that casts one of the most beautiful and enigmatic objects in our sky as the universe's ultimate courier, the comet. The concept of cometary panspermia takes the broader idea of cosmic ancestry and gives it a specific, icy face, suggesting that these frozen time capsules were perfectly designed to not only carry the ingredients for life, but to protect them on a fiery journey to a new world. A comet is far more than a simple ball of dirty ice. It is a primordial relic, a preserved sample of the very building blocks that formed the outer planets billions of years ago. Its nucleus is a porous mixture of ice's water, carbon dioxide, ammonia, and methane intimately mixed with dark, complex organic dust and dust grains. This unique composition is the first key to the theory. The ices act as a perfect preservative, a deep freeze that can keep fragile organic molecules stable for eons, protecting them from the degrading effects of cosmic radiation. Within the icy matrix of a comet's nucleus, the amino acids, sugars, and nucleobases forged in interstellar space could remain in a state of suspended animation, waiting for their delivery date. The true test, of course, is the journey's end, the violent, high-energy impact with a planet. It seems counterintuitive that anything could survive such a cataclysm. However, the structure of a comet might actually make it the ideal crash-landing vehicle. As a comet approaches the Sun, its surface heats up, causing ices to vaporize and creating its magnificent glowing coma and tail. This process, called outgassing, actually creates a fluffy, insulating layer of dust on the surface known as a crust. During an impact, this low-density, porous crust could act as a natural shock absorber. While the outer layers are vaporized, studies suggest that pockets deep within the comet's interior could experience a much milder pressure and temperature spike, allowing a significant fraction of the complex organic material within to survive the ordeal intact and rain down onto the planet's surface. We no longer have to speculate about the contents of these cosmic messengers. Our scientific expeditions have gone to them. The European Space Agency's Rosetta mission, which spent 2 years orbiting comet 67P Churyumov-Gerasimenko, provided stunning confirmation. Its onboard instruments detected a veritable treasure trove of ingredients: the amino acid glycine, the key component of proteins, and phosphorus, a vital element in DNA and cell membranes. Most significantly, it found that the comet's ratio of deuterium, a heavy form of hydrogen, in its water ice was different from Earth's oceans, suggesting that while comets may not have provided all of our water, they certainly could have delivered a concentrated dose of these other critical organic compounds. The visual is profound. Imagine a comet having drifted in the deep freeze of the Oort cloud for 4.5 billion years, nudged by a passing star into a fall toward the inner solar system. As it approaches the young Earth, its surface begins to erupt, releasing clouds of gas and dust that are rich with probiotic material directly into the nascent atmosphere. A gentle prelude to the more dramatic impact that will follow, seeding the planet with the potential for life from the depths of the cosmic dark. Now let's journey from the icy comets and deep sea vents to a surprisingly familiar landscape, the ancient shoreline. This is the radioactive beach theory, a captivating idea that suggests the very first stirrings of life may have occurred not in some exotic, extreme environment, but on a beach powered by the gentle, persistent energy of naturally radioactive sand. Picture the coast of the early Earth, a dynamic border between sea and land, constantly churned by waves and tides. But this isn't an ordinary beach. The sands here are shimmering with a faint, ethereal light, for they are rich with minerals like monazite, which contain trace amounts of radioactive elements such as uranium and thorium. The genius of this theory lies in its elegant solution to the energy problem. For life to begin, there needs to be a constant, reliable source of energy to drive chemical reactions, but not so much that it instantly destroys the delicate new molecules. The intense heat of a hydrothermal vent or the violent spark of lightning can be too much, while the cold of space is too little. Radioactive decay offers a perfect middle path, a steady, gentle trickle of energy delivered over millions of years. As these radioactive elements in the sand slowly decay, they emit alpha, beta, and gamma radiation. This isn't the cataclysmic burst of a nuclear explosion. It's a slow, consistent drizzle of energy, perfect for patiently coaxing simple molecules into more complex arrangements without violently tearing them apart. The beach environment itself provides the perfect stage for this process. Imagine the tide washing over these radioactive sands, depositing a rich soup of organic molecules that had formed in the ocean or rained down from the atmosphere. As the water recedes, these molecules are left concentrated in damp patches on and between the sand grains. The radioactive decay occurring within the monazite crystals then irradiates this concentrated organic layer. This radiation is powerful enough to break molecular bonds and create highly reactive radicals, which then eagerly snap together to form new, more complex bonds, potentially creating amino acids, sugars, and even the precursors to RNA. This isn't just a theoretical concept, it has been demonstrated in laboratory experiments. Scientists have recreated these conditions by placing simple organic precursors on synthetic radioactive minerals and observing the results. They've found that the constant, low-level radiation does indeed act as an efficient catalyst, driving the synthesis of more complex biological building blocks. The porous, granular nature of the sand provides an immense surface area for these reactions to occur, and the rhythmic cycle of wetting and drying, as the tides ebb and flow continuously, concentrates the reagents and refreshes the system. This creates a natural, planet-wide production line, with countless beaches acting as countless identical experiments, dramatically increasing the odds that somewhere the right combination of molecules would come together in the right way, all under the quiet, persistent glow of the sands that cradled them. Yet to find a truly universal laboratory, we must journey away from our planet entirely and into the vast, silent spaces between the stars. This brings us to a theory that suggests the very first steps toward life didn't happen on any world, but on the tiniest of platforms adrift in the cosmic ocean, interstellar dust grains. Envision a colossal nebula, a stellar nursery light years across, glowing with ethereal light. It appears as a beautiful, empty cloud, but it is anything but empty. It is a seething soup of gas and, most importantly, countless trillions of microscopic solid particles, silicate and carbonaceous, dust no larger than a fraction of a micron, forged in the hearts of ancient stars and scattered across the galaxy. In the deep, cold and near-perfect vacuum of space, these minuscule motes of dust become far more than just specks. They become the most fundamental solid surfaces in the universe, and they serve a critical purpose. The vastness of space is the enemy of chemistry. For two molecules floating freely to meet and react is incredibly unlikely, but these dust grains solve that problem. They act as a meeting ground, a solid anchor where atoms and simple molecules like carbon monoxide, hydrogen, and water can slowly drift in and stick to the surface, a process known as adsorption. Suddenly, instead of being light years apart, these potential reactants are neighbors held in close proximity on a tiny, frozen stage. This is where the true alchemy begins. While these nebulae are cold, they are not inert. They are bathed in the relentless energy of ultraviolet light from nearby young stars. This UV radiation doesn't just illuminate the cloud, it acts as a power source, breaking the bonds of the molecules frozen to the dust grains and creating highly reactive fragments known as radicals. These radicals, now trapped side by side on the grain's surface, are desperate to form new bonds. With the gentle warmth of a nearby star or even the faint energy of cosmic rays, they begin to hop around on their dusty home, eventually finding a partner and reacting to form new, more complex molecules. This process, repeated over millions of years, can build molecules of startling complexity right there in the void. We know this isn't just speculation because our telescopes have confirmed it. Using radio astronomy, scientists have identified a veritable menagerie of organic molecules in these molecular clouds, including ethanol, acetic acid, and even the simplest amino acid, glycine. The dust grain provides the surface, the cold temperature keeps the fragile product stable, and the UV radiation provides the energy to drive the reactions. It's a slow, cold, and meticulous form of chemistry, but it has the one thing the early universe had in abundance: time, epochs upon epochs of it. This theory paints a breathtaking picture of our galaxy not as a barren void, but as a sprawling, natural chemistry set where the fundamental building blocks of biology are manufactured on a cosmic scale, long before any planets have even formed, ready to be delivered to new worlds and become part of their story. But while the RNA world theory is a leading contender, it presents a formidable challenge. RNA is a notoriously fragile molecule. In the harsh conditions of the early Earth, its delicate structure might have been torn apart by UV radiation or hydrolyzed by water long before it could form a self-replicating system. This obstacle has led scientists to ask a profound question. Was RNA the first genetic molecule, or was it itself the product of an even simpler, more robust predecessor? This brings us to a theory that offers a compelling and elegant solution: the peptide nucleic acid world, or PNA. Peptide nucleic acid is a fascinating chimera, a molecule that beautifully blends the properties of proteins and nucleic acids. Imagine taking the information-carrying backbone of DNA or RNA and replacing its sugar-phosphate structure with something far simpler and sturdier: a chain of peptides, the very same molecules that form proteins. The nucleobases adenine, guanine, cytosine, and uracil are still attached to this peptide backbone, allowing PNA to hold genetic information and form base pairs just like RNA and DNA can. This simple swap in its architecture gives PNA some astonishing advantages for a primordial world. Its most significant strength is its incredible stability. Without the sugar-phosphate backbone, PNA is immune to hydrolysis, meaning it doesn't break down in water. It can also withstand much higher temperatures and greater extremes of pH than RNA, allowing it to persist in environments that would have been instant death for other genetic molecules. Furthermore, its neutral peptide backbone allows it to bind even more strongly and specifically to DNA and RNA than they do to each other, because it lacks the negative charge that causes electrostatic repulsion. This robust stability and strong binding make it a prime candidate for the very first molecule that could reliably store and transfer information. But could PNA have formed spontaneously on the early Earth? Laboratory experiments suggest a resounding yes. Researchers have successfully synthesized PNA monomers, its individual building blocks, from simple prebiotic chemicals like amino acids, acetylene, and formaldehyde, all of which were likely abundant. Even more compellingly, these PNA strands have been shown to self-assemble and, crucially, to act as a template for their own replication. In a warm, tidal pool scenario, a strand of PNA could line up free-floating nucleotides and guide the formation of a complementary RNA strand, or even another PNA strand, without the need for complex enzymes. This process, called template-directed ligation, is the fundamental heart of genetics, and PNA can achieve it with startling simplicity. The theory paints a captivating picture of a PNA world, where these tough, versatile molecules served as the original genetic templates, patiently and robustly building the first RNA molecules, eventually creating a sophisticated enough system that RNA could take over and launch the revolution that led to all life as we know it. Now we descend into one of the most visually spectacular and chemically potent environments ever proposed as a cradle for life, the world of the black smoker. These are not the gentle alkaline vents we discussed earlier. Picture instead a colossal, tower-like structure rising from the abyssal plain, forged from minerals and billowing a superheated, jet-black cloud of water so dense with dissolved metals and sulfides that it looks like smoke pouring from an industrial chimney. It's a scene of raw, violent power, and within this apparent chaos, some scientists see the perfect conditions for life's very first fragile steps, thanks to a remarkable geological trick, the formation of natural inorganic cells. The key lies in the specific chemistry of the fluids erupting from a black smoker. This water, heated to extremes by magma and squeezed up through the oceanic crust, becomes heavily enriched with dissolved iron and hydrogen sulfide. When this scorching, chemical-rich fluid blasts out into the frigid deep seawater, an instantaneous and dramatic change occurs. The minerals, now suddenly cooled, precipitate out of solution at a staggering rate. One of the most important precipitates is iron sulfide, primarily in the form of pyrite, commonly known as fool's gold, and this is where the magic happens. Laboratory experiments have shown that under conditions mimicking these vents, iron sulfide does not simply form a solid lump. It can spontaneously precipitate into microscopic bubbles and honeycomb-like structures. These are not organic cells, but they are compartments, tiny, self-assembling, mineral-lined chambers that create a crucial separation between an internal and external environment. Imagine these microscopic iron sulfide bubbles forming by the trillions in the turbulent, mineral-rich plume around a black smoker. Each one of these tiny compartments acts as a natural laboratory, its semi-permeable mineral walls selectively concentrating the organic molecules that are also forming in the vent's intense heat and pressure. Inside this protected space, the conditions are ideal for the kind of chemistry life requires. The iron sulfide walls are not passive. They are catalytic and electrochemically active, capable of facilitating redox reactions, the same kind of electron transfer reactions that power all modern metabolism. A molecule like pyrite has a crystalline surface that can donate and accept electrons, effectively acting as a primitive, inorganic enzyme, driving cycles of reactions that could have led to the first metabolic processes. In this view, the first cells were not made of lipid, They were made of stone, providing the sheltered, organized space where chaotic chemistry could begin to organize itself into something far more sophisticated. The most compelling evidence for this theory isn't just in a lab, it's thriving all around these vents today. Black smokers and their relatives are oases of life in the deep sea desert, supporting lush ecosystems that exist in total independence from the sun's energy. The foundation of these ecosystems are microbes that perform chemosynthesis, deriving their energy not from sunlight, but from the chemicals spewing from the vent specifically by oxidizing hydrogen sulfide. These microbes then form the base of a food web that includes gigantic tube worms, blind shrimp, and unique clams, all perfectly adapted to this high-pressure, pitch-black, and chemical-rich world. The existence of this entire sunless biosphere is a powerful proof of concept. It demonstrates that complex life can not only survive but flourish by harnessing the geochemical energy of a hydrothermal vent, using the same basic principles that the iron sulfide world theory proposes were in place billions of years ago. It suggests that the leap from geochemistry to biochemistry might not be a fantastical jump, but a natural continuation of planetary processes, with the towering, smoke-belching black smoker standing as a monument to that profound transition. Now let's lift our gaze from the deep oceans and radioactive shores to the very skies above the primordial Earth, to a theory that finds life's origins not in a single location, but in a planet-wide phenomenon. This is the concept of atmospheric aerosol reactions, which proposes that the first steps toward life occurred in countless tiny, suspended droplets within the ancient atmosphere, essentially turning the entire sky into a massive, diffuse chemical laboratory. Imagine the early Earth's atmosphere not as a clear, empty expanse, but as a perpetual global haze. It was thick with water vapor, methane, carbon dioxide, and nitrogen, constantly churned by volcanic eruptions and electrical storms. Within this soupy mix, microscopic droplets of water and other liquids would have condensed around fine particles of dust, salt, or volcanic ash, forming a permanent aerosol mist, a lot like the clouds we see today, but far more extensive and chemically rich. Each one of these trillions upon trillions of floating droplets acted as its own isolated miniature reactor, perfectly designed to overcome one of the biggest hurdles in the origin of life, concentration. In the vast, dilute ocean, the chance of two specific molecules meeting is incredibly slim. But inside a tiny aerosol droplet, the rules change completely. These droplets naturally concentrate any organic molecules that form in the atmosphere or are delivered by meteorites, pulling them from the diffuse gas and gathering them into an incredibly dense, intimate mixture. It's the difference between trying to mix a single drop of food coloring into an entire swimming pool versus into a shot glass. In the shot glass, the reaction is immediate and intense. Within each droplet, the building blocks of life are forced into close contact, dramatically increasing the odds that they will collide and form the bonds needed to create more complex chains like peptides and nucleotides. But these droplets offer more than just concentration. They provide a unique and powerful energy source. The young sun bathed the planet in intense ultraviolet light, and these suspended droplets were perfectly positioned to harness it. The curved surface of a droplet can act like a tiny lens, focusing the UV energy into its core. This concentrated light could then drive photochemical reactions, breaking apart molecules inside the droplet to create highly reactive radicals that would eagerly snap together into new, more complex configurations. Furthermore, the constant cycling of these droplets evaporating and recondensing as they moved through different layers of the atmosphere created a natural rhythm of wet and dry phases. This cycling is crucial for driving dehydration synthesis, the chemical process that links small molecules together into long chains by removing a water molecule, a reaction that is notoriously difficult to achieve in a constantly wet environment like the open ocean. Scientists have tested this captivating theory in the laboratory with remarkable results. researchers create chambers that simulate the proposed primordial atmosphere filled with water vapor and simple gases. They then introduce an energy source, often a UV lamp mimicking the young sun, to create reactions. The results show that these aerosol conditions are exceptionally efficient at producing a wide range of biological building blocks, including amino acids and the nucleobases that form RNA. The droplets not only facilitate these reactions but also protect the fragile new molecules. Once formed, they are encased in a protective shell, safe from the very radiation that helped create them until they eventually grow heavy enough to fall as rain, delivering their precious organic cargo to the oceans and lakes below. This theory transforms our view of the early atmosphere from a passive blanket of gas into an active, creative engine, a global mist that patiently assembled the Lego bricks of life one droplet at a time, showering the young Earth with the promise of biology. But if thioesters provided one possible early energy source, another candidate is waiting in the wings, a molecule so fundamental to modern life that its energy currency still powers every single cell in your body right now. This brings us to the world of polyphosphates, and a theory that suggests the very first metabolism might have been powered by the humble, yet incredibly energetic phosphate bond. To understand why this is so compelling, we need to look at the universal energy coin of all known life, ATP, or adenosine triphosphate. Inside you, right now, ATP is constantly being spent to power your muscles, your nerves, your very thoughts. Its power comes from its 3 phosphate groups linked together in a chain. Breaking the bond that holds the last phosphate group releases a burst of energy that cellular machinery can harness. But ATP is a complex, evolved molecule. The polyphosphate theory asks a brilliant question. What came before ATP? The answer may lie with much simpler chains of phosphates, forged not by biology, but by the geology of the early Earth itself. The beauty of this idea is its simplicity and its power. A polyphosphate is just a linear chain of many phosphate groups linked together. The bonds between these phosphates are high energy, much like a tightly coiled spring. When that spring is released, when the bond is broken, it unleashes energy that can drive other chemical reactions. This is the absolute core of metabolic energy, and polyphosphates are exceptional at it. But the crucial twist of this theory is that the first polyphosphates might not have needed a complex biological factory to produce them. They could have been made readily available by the planet itself. Geochemical processes are incredibly efficient at creating these molecules. For instance, the mineral schrebersite, commonly found in iron-nickel meteorites, can react with water to release phosphate and spontaneously form these energy-rich polyphosphate chains. Volcanic activity can also create polyphosphates through the simple heating of phosphate-containing minerals. So imagine the early Earth constantly being seeded with these energy-rich molecules from incoming meteorites, while its own volcanic fires manufactured more, creating a planet-wide reservoir of ready-to-use chemical energy, simply lying around for any nascent chemical system to exploit. This available energy source could have been the catalyst that kicked everything into gear. In a warm little pond or at a hydrothermal vent, these geochemically produced polyphosphate chains could have provided the power to drive essential early reactions. Think of a simple amino acid floating in the primordial soup. On its own, linking with another amino acid to form a peptide bond is a difficult, uphill chemical reaction. But in the presence of a polyphosphate, that reaction gets a powerful push. The energy released from breaking a phosphate bond could provide the necessary activation energy to force 2 molecules together, building complexity step by step. This process, called phosphorylation, is how modern cells activate molecules and build complex structures, and it might be an ancient echo of life's very first method of doing work. The theory suggests that before there was a sophisticated system to make energy, the first proto-metabolic networks learned to use the energy that the geology of the planet was generously providing for free. building their complexity on the back of these geochemical batteries until they were sophisticated enough to eventually make their own. However, to truly stretch the boundaries of this cosmic detective story, we must consider one of the most audacious and fringe ideas of all. That life did not begin on Earth at all, but on our closest celestial neighbor. This is the lunar origin hypothesis, a theory that proposes the first living organism might have sparked into existence on the early moon, only to later hitch a ride to our planet on a piece of rock blasted into space by a colossal impact. It's a concept that sounds like pure science fiction, but it forces us to confront some fascinating possibilities about what makes a world truly habitable. The logic behind this idea hinges on a few key advantages the young moon might have possessed over the young Earth. Billions of years ago, shortly after the moon formed from the debris of a giant impact with a Mars-sized body called Theia, it was a world of dramatic contrast. It likely had a temporary, thin atmosphere outgassed from its still molten interior and was much more geologically active than it is today. Crucially, however, it lacked the two things that made the early Earth so violently chaotic: a thick atmosphere and vast, churning oceans. Without these, the moon's surface would have been a far more stable environment. It would not have been subjected to the constant erosion of wind and rain, the planet-wide dilution of a global ocean, or the immense atmospheric pressure and hurricanes that raged on Earth. This stability could have been a major benefit, allowing delicate chemical processes to proceed for long, uninterrupted periods in certain protected niches. One particularly compelling lunar environment could have been its ancient lava tubes. These are massive, cave-like tunnels formed by flowing lava, and they have been discovered in abundance on the moon. Shielded from the harsh vacuum of space and the sun's lethal ultraviolet radiation by a thick roof of rock, these subsurface caverns could have created stable, protected microclimates. Within them, perhaps fed by localized water ice or geothermal seeps, the same prebiotic chemistry we've discussed for Earth could have taken place, but with a crucial difference: a lack of disruptive forces that might have constantly dismantled progress on our more dynamic planet. In these silent, dark, and stable lunar caves, the slow, patient work of building complex organic molecules might have had a better chance of reaching a critical threshold. Of course, the challenges are immense and likely insurmountable. The most glaring issue is water. Liquid water is the universal solvent of life as we know it, essential for nearly every biochemical reaction. While we now know the moon has water ice frozen in permanently shadowed craters at its poles, maintaining large, persistent bodies of liquid water on its surface without a substantial atmosphere to create pressure and trap heat seems nearly impossible. Any water would have instantly boiled away in the vacuum or frozen solid in the deep cold. The moon's lack of a strong magnetic field also left it utterly exposed to the full fury of solar radiation, sterilizing its surface and making it an incredibly hostile place for any fragile chemistry. Furthermore, the shorter geological lifespan of a smaller body meant its internal heat engine, which could have powered hydrothermal systems, faded much more quickly than Earth. But let's entertain the thought experiment. Suppose against all odds that a self-replicating system did emerge in a protected lunar haven. How could it possibly get to Earth? The mechanism is one we've already explored: impact ejection. The early solar system was a shooting gallery, and the moon's surface, preserved and unchanging, is a stark record of that bombardment. A large enough asteroid impact on the moon would have been utterly cataclysmic for any local biology, but it could have also blasted tremendous amounts of crustal material into space. If that material contained within it our hypothetical lunar microbes, sheltered deep inside the heart of a rock, some of it could have been flung on a trajectory that intersected with Earth's orbit. The journey through space would be a trial of radiation and cold, but as we know from the study of extremophiles, some organisms can enter dormant states of incredible resilience. After a journey of perhaps years or decades, these lunar meteorites would have screamed into Earth's atmosphere. While the outer layers would have vaporized, creating a brilliant fireball, the interior could have remained cool enough to protect its microscopic passengers, allowing them to crash land safely in the early Earth's welcoming, warm, and water-rich oceans, a new world ripe for colonization. This incredible scenario, while deeply speculative, challenges our planetary chauvinism and expands the stage upon which the grand play of life's origins might have been performed. After our incredible journey through cosmic clouds, deep sea vents, and even the possibility of a lunar beginning, we arrive at a compelling modern perspective that doesn't choose just one theory, but seeks to weave them all together. This is the world of hybrid and emerging theories, where scientists are no longer asking which environment was the cradle of life, but how many of them worked in concert, each playing a crucial role in a grand planetary-scale recipe for biology. The current frontier isn't about finding a single smoking gun. It's about understanding the entire orchestra of processes that could have turned geochemistry into biochemistry. This integrated approach is often called systems chemistry, and it changes the entire framing of the question. Instead of a single linear path, it envisions an intricate network where products formed in one environment were transported to another, where each step added a new layer of complexity. Imagine amino acids formed by electric sparks in the atmosphere, raining down into the oceans. These molecules are then concentrated in tidal pools through wet-dry cycles, where they link into peptides on the surface of clay minerals. These more complex compounds are then washed into the deep ocean, where they become encapsulated inside lipid vesicles that formed near hydrothermal vents. Inside these protected bubbles, fueled by the natural proton gradient of an alkaline vent, they finally begin to exhibit the first signs of metabolism and replication. No single location did all the work. Each one acted as a specialized factory on a planetary assembly line, contributing its unique product to the next stage of the process. The most exciting work testing these hybrid models is happening in laboratories around the world, where researchers are building increasingly sophisticated simulations of the early Earth. These aren't simple glass beakers, they are interconnected reactor systems that mimic different environments, literally piping the products from one chamber into the next. In one vessel, they might simulate an atmospheric aerosol reaction using UV light, creating a spray of organic compounds. This mist is then channeled into a second chamber that replicates a warm, evaporating tidal pool, encouraging those molecules to form longer chains. The resulting solution might then be dripped into a third reactor that mimics the pressure and chemistry of a deep-sea vent, complete with mineral catalysts and lipid molecules that spontaneously form protective vesicles. These experiments are breathtakingly complex, and they are starting to show that this multi-stage, multi-environment process isn't just possible. It might be significantly more efficient and robust than any single origin story alone. This work naturally dovetails with the explosive field of protocell research, the attempt to literally build a primitive, synthetic form of life from non-living parts. The goal here isn't to create life in a test tube for the sake of it, but to reverse engineer the simplest possible system that can meet the definition of being alive, something that can maintain itself, metabolize energy, and replicate. Scientists aren't starting with complex DNA, they are starting with the very building blocks we've discussed. They create lipid membranes that can grow and divide. They design short strands of RNA that can catalyze their own replication. They engineer simple metabolic cycles that can generate energy. The ultimate aim is to combine these components into a working whole, a protocell. Each successful experiment, even a partial one, acts as a proof of concept, showing that a particular step in the journey from chemistry to biology is not only plausible but demonstrable. These synthetic life experiments are like historical reenactments, testing the viability of the various scripts we've imagined for life's origin. What emerges from all this modern research is a profound shift in perspective. The answer to the universe's first living organism likely isn't a single, elegant theory waiting to be crowned the winner. The answer is probably messy, contingent, and beautifully complex, a fortunate convergence of countless processes across a wide range of environments on a young, active planet. It suggests that life is not a single moment of miracle, but a threshold, a phase transition that matter can cross under the right conditions. This holistic view doesn't diminish the wonder of our existence, it amplifies it. It paints a picture of a universe rich with potential, where the ingredients and the energy and the environments are all available, waiting for the right combination to stir itself awake, transforming the cosmos from a silent void into a living, breathing, and questioning place. And so, after this epic journey across 30 different landscapes of thought, where does that leave us in our search for the universe's first living organism? We've ventured from the crushing, mineral-rich depths of hydrothermal vents to the icy, silent laboratories of interstellar space, from the electric fury of primordial skies to the quiet, persistent glow of radioactive beaches. We've seen life potentially begin in warm little ponds on the surfaces of clay crystals, within the protected bubbles of lipid membranes, and even as a deliberate gift from beyond our stars. The sheer diversity of these ideas is not a sign of confusion, but a testament to the incredible creativity of science and the profound depth of the mystery itself. Each theory, from the rigorously tested to the wondrously speculative, adds a crucial piece to the puzzle. They are not necessarily competitors, but rather different chapters in the same grand story, a story that suggests the path from non-life to life may be less of a single, miraculous leap and more of a winding, planetary-scale journey with many possible on-ramps. What this incredible tapestry of ideas truly reveals is a universe that seems almost eager to become alive. The building blocks are everywhere, forged in the hearts of stars, assembled on cosmic dust grains and delivered by comets. The energy sources are abundant, from the sun's relentless UV rays to the gentle decay of radioactive atoms and the fierce geothermal heat of a young planet. And the environments that can concentrate, protect, and organize these ingredients are countless. This doesn't make the origin of life a simple or inevitable process, but it does reframe it from a near-miraculous accident into a phenomenon that the laws of physics and chemistry are deeply capable of producing. The universe appears to be a participant in this great unfolding, not merely a backdrop. Ultimately, this quest for our cosmic beginnings is about so much more than biology or chemistry. It is a fundamental part of the human story, our attempt to find our place in the cosmos and understand where we came from. For millennia, we have looked to the stars and told stories of our creation. Today, we are writing a new chapter in that epic, using the tools of science to test those stories against the fabric of reality. Whether the first spark was a chemical reaction on a pyrite crystal or a molecule replicating in a tidal pool, the search itself is a beautiful expression of our curiosity and our deep, enduring desire to connect with the universe that gave us birth. This is our shared origin story, and every new theory, every experiment, every discovery brings us closer to understanding our own profound connection to the cosmos. Now, we want to hear from you. After exploring these 30 theories, which one captures your imagination the most? Do you find the elegance of the RNA world convincing, or are you drawn to the epic scale of Panspermia? Does the simplicity of the lipid world feel right, or does the quantum mystery spark your curiosity? Let us know your favorite in the comments below. We love diving into these discussions with you. And if you enjoyed this journey to the very edge of what we know, make sure to subscribe and hit the bell so you don't miss our next exploration into the great mysteries of space, time, and existence. Thanks for watching.